Hi folks, this is Stan Forrester. We're working in Module 2 now, and one of the questions you're asked is how can you use a tool like Excel to estimate what, say, the maximum range of something is. Okay, now what I'm going to do is I'm going to go ahead and just do the very simple formulas for projectile motion without air friction. Okay, and so we know that the maximum range is going to be something like 45 degrees. You can work that out. Okay, but the first thing, I'll post this spreadsheet later for you to work with. Okay, so what we have here is we have delta t, which is the simulation time. Okay, we're going to take a look at this in time steps of 1/100th of a second. Okay, so each second is the previous time plus whatever that time step is. Right here we have the acceleration in the x direction, the horizontal acceleration due to gravity, which is 0, of course. Downward in the y direction, minus 9.8. Notice that when I say minus 9.8, I'm implying that upwards is positive. I go ahead and I calculate the velocity, which is going to remain the same in the x direction. The x component of the velocity is going to remain the same. The y component, however, is, notice I use the same formula here. It's just that the acceleration is 0, and so that the velocity stays the same. Here I use the same formula. I've got a different acceleration. I've got a negative acceleration, and so the y component of the velocity is going to be a little bit less each time. Okay, and eventually it's going to, of course, reach 0. That's the top of the arc. It's not going to go up any further, and that'll be the max height. And so, of course, we could look for that. Where let's see, where is that 0? It is 0 someplace. Okay, so right here, or somewhere right in here, so about 8.27 seconds or 8.28 seconds, it passes through 0 velocity. That would be the time to reach the maximum height. You can go ahead and run these numbers yourself, all right, and see if that comes up with something even reasonable. Here's my x and y position. Okay, here we have, let's say, okay, I have the previous position. Okay, G7 is the previous position, and I add to that a change in position due to the velocity plus a change in position due to the acceleration. Okay, and this is, let's make sure that I put that there. Okay, okay, I almost changed the formula. Okay, and again, there's y here, but here in y again, we're going to have that that there's negative acceleration, and so even though this is rising upward, it's got a positive velocity, that amount of increase each time is going to get a little smaller each time. Okay, so let's see if we can't plot the x versus y position, at least until the y position comes back to 0. Okay, this is going up pretty far here, 300 meters. Starting with 100 meter per second initial velocity. Notice the y position, it's coming down now. Okay, so let's see if we, there. Somewhere about 16 seconds, 16 and a half seconds, it's getting ready to pass through the initial position, y equals 0. It's coming back to the same initial height, and that matches our intuition. If it took about 8 and a bit seconds to rise to the maximum height, it's going to take about 8.5 seconds to fall back to that original height. Now, if the final height is somewhere below that, let's say 10 meters below that, it's going to have an additional time to fall. Okay, so it's a minus 10 meters below the initial position. It's going to take a little more than 16 and a half seconds to fall to that position. But let's go ahead and let's just plot this here. Okay, I'm going to highlight the x and y position there. This is the x and y position as functions of time. And I'm going to insert a chart. It's a scatter chart. All right, and we don't really have to plot a trend line here. We don't have to plot a trend line here because there's so many plots pointed that they just all kind of blur together and it looks like this great big line. One thing to look at, though, is that we have values here that change very rapidly on either side, but where the velocity is small, we're going to see that this curve kind of flattens out here. And now we're going to take advantage of that in the next sheet. In the next sheet, we're looking at the range formula. This is the range formula over level ground. This is the velocity squared times sine of 2 theta over divided by the divided by g. Again, we're starting with 100 meters per second. We have this formula all plugged in here and ready to go. And then what we're going to change here, instead of changing the time, we're going to change the angle a little bit. Okay, now you can play with this. You can put in another formula. Say there's a more complicated formula for range over non-level ground. There's a whole other term that follows all this. And then you could see which theta is going to give you the maximum range. Okay, so if we take a look at this, I could plot theta from 30 to 60 degrees here. One thing you'll notice here is that when you put degrees into a formula like sine, you have to use this pi divided by 180. That's a conversion. Okay, so the formulas, the trig formulas in Excel expect to receive something like something in, oh goodness gracious, expect to receive a value in radians. Okay, so you have to convert those degrees to radians before you do that. All right, so at 30 degrees, 100 meters per second, we expect a range over level ground of 883, and we see that that's down here someplace. But as the angle increases, so does the range up to some point. Now, we know just from experience, I mean, your kid throwing rocks and things like that, about 45 degrees is pretty much where you're going to get that that maximum range. But as we come up here, we're going to look for that flat spot. There's that flat region. I'm going to call it somewhere between 40 and 50, and I could just take and change this formula so that we go from 40 to 50. But you know something? I'm just going to go over here. I've copy and pasted that formula over to here, and I go 41, 42, and we can see that 1, 2, 3, 4, 5. Yeah, indeed, it is 45. What if we wanted to make that? What if we wanted to make that investigate even smaller degrees of angle? So 0.1, 40.2. So we've got even smaller gradations of degree here. Oh, it should be 40.2. Grab Nebbit. There we go. Yeah, let's make it a little more than that. Maybe not quite that small. Okay. Well, in any case, we can see that when we make the difference in degree even smaller, we can still calculate that formula. Let's go ahead and do this. This is 44.2. Make this 44.4. All right, and we're plotting these points here, and we can see again that 45 comes out to be the maximum. Anyways, that's just one way that you can use Excel for this sort of thing. We could actually plot the trajectory. That showed you that, and we can investigate maximum and minimum values as we change a parameter like angle, launch angle. Okay, I hope this was somewhat helpful. I will post this worksheet where you can get to it, and good luck with your discussion questions.